Hey everyone, we're looking at a new scenario today in static equilibrium. The problem you're seeing here with the person seeing the $100 bill and trying to push over that big marble slab without tipping it reminds me a lot of what we did in class. It kind of looks like cow tipping. So if you wanted to tip the cow, we did calculate the amount of force it takes to push a cow over. And if you want to watch the video from Big Bang, just click here. In this scenario, you can see the applied force from the person is going to be just above the center of gravity, and they're going to try and tip it so that the weight comes off the $100 bill, and really the forces are the static friction and the normal force on that back corner. So you can imagine like a filing cabinet that being tipped, where this bottom corner is the only point of contact so that you can reach and grab things from underneath. The object is still in equilibrium, not a stable equilibrium, but it's still static. Every force would be balanced, every torque would be balanced, and the object would not rotate until you release your applied force and the block comes tumbling back to its original state. But in this scenario, what we want to look at is what happens when we have static equilibrium in accelerated frames. So what that means is our first rule is going to change. The first rule always said that our sum of forces must equal 0. But in this case, the sum of forces will equal ma, but the torques will still cancel out to 0. So the example is from that big block. Let's say you put a big block in the back of the truck there and accelerate away. The door is open for whatever reason, you didn't shut the door. The question is, how quickly can you accelerate so that the block does not tip over? The block still does not rotate, so there's no rotational motion to it, but it can still have straight line linear acceleration and move with the truck. So let's draw a force diagram and show what this would look like. Okay, so if we've got the block here, it's got a length of L, and we have it sitting in the back of the truck and the truck is not moving. So if it's not moving, then we know there's no acceleration and the block should be stable. So if I look at my forces, that should be pretty easy to analyze. I've got the force of gravity acting straight down at the center of gravity, and I've got the normal force from the ground pushing back up with an equal and opposite force. Those two forces cancel, so my sum of forces is 0. But if we start to accelerate and we see that the block starts to tip, as it starts to tip, the normal force is going to shift from right underneath the center of gravity to that back corner. So the normal force is going to act right here. So if you look at our sum of forces, our y forces are still canceling to 0. We've got our force of gravity down, we've got our normal force up, and those two do still cancel out. However, now that it's tipping and the whole car is accelerating forward, we need a net force forward to make this thing accelerate. And the force that's going to try and resist it from sliding backwards and tip is the force of friction. So there's going to be friction from the ground pushing forward, causing the block to accelerate. So the first thing I could say is that, alright, friction makes my mass accelerate. But we also want to show that since this is tipping but not rotating, the angular acceleration is 0 and our net torques cancel out. So let's look at the torques acting on our box. And for this scenario, what I'm going to do is I'm going to make my pivot the center of the block. And I'll show you why there's reasons for me putting it there rather than down in the corner. If I put it in the corner, I eliminate the normal force and the friction, and there's no torque. And the only thing torquing this is the box's own weight along this line, trying to make it go back down to have its end flat on the car. But since I need to know what this force of friction is that makes us accelerate, I'm going to look at the center of gravity as my pivot point. And when I do that, what I can say is that, well, I see that friction and the normal force are acting at distance away from the center of mass. And remember, I care about them being perpendicular to my rotation point. Well, the normal force is acting at a distance d away from the pivot. So if I look at summing my torques and making my torques still add up to 0, because that rule still applies, I'm going to have 0, and if I do an R cross F, I get a negative torque from the normal force multiplied by that distance, and that distance actually happens to be half the length of the block. Okay, well, where is the frictional force acting? Well, the frictional force is acting at a distance of right here. It's acting that far away from the pivot point. So it's half the height of the box. And if you do an R cross F there, you get a positive torque for friction. So I'm going to add the force of friction multiplied by half the height of the box. And that's going to give me my equal and opposite torque down in that bottom corner. These two are going to cancel each other so the block doesn't rotate and fall out the back of the truck. Again, our total goal here is to solve for the acceleration of the system. If I look at my sum of the y forces, that's pretty easy. The y forces are just the force of gravity and the normal force. We know those two have to equal each other. So in my equation here, I can replace normal force with the weight of the block, mg. And we said what's making this whole thing accelerate? It's friction. So I'm going to eliminate friction down here with ma. And since those torques must be equal and opposite, I can say that those two must be equal. And this is what you get. Get mg times half the length for the torque of the normal force, and you get ma half the height for the torque from friction. What you can see is that we don't need the mass of the object to find this acceleration, and I actually don't even need the 1/2. So if I want the acceleration is a ratio of g multiplied by the length over the height. And that is how quickly we can accelerate without having the block topple out of the back of the truck. So what does that mean? Well, if the length of our block is smaller than the height, that means our height is bigger. It's going to decrease the acceleration that we can have. You're going to have to accelerate slowly if the block is standing up tall. So how could we accelerate faster? Say you were trying to steal that giant block of marble and you put it in the back of a truck and you wanted to accelerate and get away from the scene of the crime quickly. Well, you'd want to decrease the height and increase the length. How can you do it for that block? Carefully lay it down in your car, and now the height is much smaller than the length. And in that case, if the height is much smaller than the length is very large, and you can have a much larger acceleration to get away and steal that very large block of marble. Another way of thinking of this, the center of gravity here in the center is over a very tiny base. So it being over a tiny base doesn't have a lot of wiggle room in terms of tipping. But in this case, we lower the center of gravity closer to the ground. And when we lower the center of gravity closer to the ground, it's harder to tip and twist something with a low center of gravity versus a high center of gravity, which will be a topic for next time.